In this lecture, we'll talk about the linear momentum equation, and specifically for an inertial frame of reference. In a later video, we'll talk about non-inertial frames of reference, and I'll explain what that means in a little while. The linear momentum equation really is just a statement of Newton's second law. In a previous lecture, we talked about conservation of mass. Now we're going to move on to Newton's second law. And what I'd like to do is, in this lecture, is derive the equation that we're going to use, so linear momentum for control volumes, and then we'll talk about some of the assumptions and how to apply the equation. And I'll have examples in separate videos. Let's start, first of all, with some motivation. If you look at your screen, you'll see a picture of a 747, and specifically I want to focus on the jet engines there. And the reason for that is because jet engines operate using the principle of linear momentum. The idea is this, so go ahead and look at your screen. The jet engine, let me go ahead and sketch it out here. Looks something like this. Here it's connected to the wing. We have some flow coming into the engine, and it goes out with a much higher speed. Now, if you recall from Newton's second law applied to a system, that any time you have a change in linear momentum, there must be some force that acts on that system. Let's go ahead and write that down. So, time rate of change of the linear momentum of a system, and remember, linear momentum is just a mass times velocity. So if we have a time rate of change of that linear momentum, there must be some force that caused that change in linear momentum. So back to the picture, you'll see that there's some linear momentum of the airflow coming into the engine, and that linear momentum is relatively small. It comes in with a relatively small velocity, but when it goes out, it has a much higher velocity. So that linear momentum is changed. What's caused that change in linear momentum? It's the force that the engine exerts on the surrounding air. Now, from Newton's third law, if the engine has exerted some force on the air, then the air exerts an equal and opposite force on the engine. That force that's applied to the engine eventually gets transmitted to the rest of the plane through the structure on the engine, up through the strut and through the wing and to the rest of the aircraft. That's what provides the thrust for the aircraft to move along. So the purpose of the jet engine is to change the air's linear momentum, which then provides the thrust for the aircraft. So we'll talk a little bit more about linear momentum in this lecture, and you'll see it in many of the examples. I wanted to show a little video that demonstrates the high speed of the air that comes out of the back of the engine. It's pretty dramatic. Here we are. So you'll see this is a stage demonstration. There's a little vehicle that's going right behind. You can see it's empty. It's going right behind the jet engine. And the jet engine's at high throttle. I think it may be at full throttle. And you can see the air blast coming out of the back of the engine. It's very powerful. Tumbles the truck into the water. We'll see a few different versions of this because it's so dramatic. It's kind of neat to look at. Obviously, never walk behind a jet engine while it's operating. That would be a bad thing to do. But I just wanted to show this because it's pretty impressive, the high-speed air that comes out of the back of the engine. We'll let it finish here because it's kind of fun to watch. All right, very good. Let's go ahead and get back to our lecture materials. So we're going to start by deriving the linear momentum equation, and we're going to do this by starting with the system. As you know from the Reynolds transport theorem and our derivation of conservation of mass, it's easier to write the governing equations for a system point of view and then use the Reynolds transport theorem to convert them over to a control volume point of view. So we'll start here in the picture. We have a system of fluid, that's the dashed line here. We have a bunch of little pieces of fluid that I've shown here. We're going to use this coordinate system, the capital XYZ coordinate system. This is an inertial coordinate system. What that means is that it's not accelerating. So it's either fixed in space or it's moving in a straight line at a constant speed. Both of those are non-accelerating. It has to be, that means inertial if it's not accelerating. In a different lecture, we'll focus on non-inertial frames of reference, but here it's inertial. Okay, so what we'll do is we'll get the linear momentum of the little pieces of fluid relative to that coordinate system. So here's one piece of fluid. It has a velocity u, x, y, z measured with respect to that coordinate system, that inertial coordinate system. So there's the velocity of that piece of fluid, and the mass of that little piece of fluid is rho dv. It's the differential volume because it's just a small piece of fluid. So that's the linear momentum of that small piece of fluid. Now if you notice, these other pieces of fluid have different velocity vectors, so they could all have different momentums. They could have different densities, so they'd have different masses. And since they could have different velocity vectors, different magnitudes, different directions, they could also have different linear momentums. So when we write down the linear momentum, or Newton's second law for this system, it'll look like the following. So the time rate of change of the linear momentum of the system is equal to the net force acting on that system. But since we said that the linear momentum, all the little bits of fluid could be different, we should write this in terms of an integral to allow us to have that variation. So we'll write it this way. This is the forces. I should probably write subsystem here so that we know these are the forces acting on the system. And then I'm going to write it like this. So what we have here is, this is the time rate of change of the linear momentum of the system. And I'm using that capital D dt notation. If you recall from the Reynolds transport theorem, that capital D dt notation is just an indicator that we're following a system. It's just a notational indicator. So it's the time rate of change of the linear momentum of the system, where that linear momentum of the system is written in terms of an integral to take into account the possible variations from fluid element to fluid element. So we have the velocity of the fluid element, the u, x, y, z. It's again the velocity measured using our inertial coordinate system, multiplied by the little bit of mass of that little piece of fluid. And that gives us a linear momentum, and then we add it up over the entire volume of the system. And that time rate of change of linear momentum will equal the net force acting on that system. So that's just Newton's second law written for a system. Now what we're going to do is use the Reynolds transport theorem, and I've shown that right here on the screen as a reminder. So we're going to use the Reynolds transport theorem to convert it over to a control volume point of view. Now the left-hand side looks like the right-hand side of the equation up here. We've got the d dt term, then we have this integral. Here beta is the velocity. Remember, beta is some transportable quantity per unit mass. Here that transportable quantity is linear momentum. So linear momentum is like mass times velocity. So beta is the quantity per unit mass. It would just be the velocity. The masses would divide out. So I'll just write it here to make it clear. So beta again is the momentum per unit mass. So this is this part of the equation. It's the same as that side of the equation. So let me go ahead and put in here is the force. Right, so all I've really done is rewritten the Newton's second law for the system here. But now I'm going to make use of the Reynolds transport theorem to convert the left-hand side of the equation. Let me write it over here. All right, so what I've done is I've just taken the Reynolds transport theorem and written out the control volume side of the equation. We're going to do just one more, maybe a couple more steps before we stop, and then I'll describe all the various terms in the equation. The next step that I'm going to do is I'm just going to rewrite the forces acting on the system. So remember that when we apply the Reynolds transport theorem, the system and the control volume are coincident, meaning they're in the same place at the same time. So any forces that act on the system are the same forces that are acting on the control volume. So I can rewrite this forces on the system as forces on the control volume. So that's one thing I'm going to do. The second thing I'm going to do is I'm going to expand those forces into two different kinds of forces. We're going to talk about body forces and surface forces. And I'll explain what those are in a moment. But I'm going to break the forces into two parts. So let me rewrite the equation. And then I'll explain what each term represents. Okay. This, let me go ahead and box it in because this is our final form of the equation. This is the linear momentum equation, LME, for a control volume using an inertial frame of reference. Again, inertial frame of reference just means not accelerating. Like a non-accelerating control volume, or coordinate system, sorry. All right, let me explain what each of the terms represents in that equation. So I'll start on the left-hand side, and then I'll work my way to the right. So the first term, right here, is the time rate of change of linear momentum within the control volume. So this is, write it down here, this is the rate of change of linear momentum in the control volume. All right, and the reason I know it's within the control volume is because of the integral is a subscript CV. It means I'm integrating for all of the elements within the control volume. In fact, let me draw a control volume over here. So here's our control volume. That's the inside. That's our control surface. So I'm going to highlight the yellow here. Yellow just means all the stuff on the inside. Okay, so it's all the velocities times little bits of mass, everything on the inside, and I see how that changes with time. And that's what that first term represents. Now the second term is the flux of linear momentum out of the control volume through the control surface. So this is the net flux of linear momentum out of the control volume through the control surface. It's just the little pieces of fluid may leave the control volume, right, through the control surface, and when they leave, they take some of their linear momentum with them, right? So we're losing some linear momentum because pieces of fluid are leaving, but we also may be getting some linear momentum as new pieces of fluid come into the control volume. So that's what this term represents, is the flux of linear momentum, the net flux of linear momentum out of the control volume through the control surface. Remember that this term in parentheses here is just a little bit of mass flow rate. It's just the density times the relative velocity dot product with the area. So that's the same thing that we had in conservation of mass, just the mass flow rate. Now this integral occurs over the control surface. So I'm going to highlight that in pink here to indicate that it's over the control surface. So that's just for the little bits of fluid on the surface here. Okay, so this velocity u here is for the velocities on the surface. That's very important to remember. You have to. This is a common mistake that students make, is getting confused which velocities correspond to which integral. Just the pink ones that I show on the screen here are for the control surface because the integral is over the control surface. The yellow ones are, oops, I made a mistake there. Let me fix that. The yellow velocities are within the control volume, so everything on the inside of the control volume. All right, very good. Let me just also remind you this U relative, I'm going to highlight that in green. Remember that U relative, let me write that down here, U relative is just the velocity of the fluid, so here would be the velocity xyz minus the velocity of the control surface. Okay, so it's the velocity of the fluid relative to the control surface at the surface. Okay, that's the relative velocity. If the control surface isn't moving, then it's just going to be the same velocity as the uxyz. It's just the same velocity of the fluid because the relative velocity is the fluid velocity minus the control surface velocity at the control surface. So if the control surface doesn't move, then it's just the fluid velocity. So I'm going to highlight that one in pink again. Because that's the same velocity as the other one that's highlighted in pink. All right, now let me move on to the next term. This one, the F sub b, these are body forces acting on the control volume. So body forces are the forces that act on all parts within the control volume. So gravity and electromagnetic forces are examples of body forces. So gravity acts on the entire volume of material, all the little bits on the inside. If you were dealing with a material that was maybe had some iron to it and you applied a magnetic field to it, then those magnetic forces would affect all the little bits of iron on the inside of the control volume as well. So those are examples of body forces. So in this class, we'll deal almost exclusively with just gravity. So our only body force will typically be the weight. Okay. And then the very last term, these are surface forces. So surface forces are the forces that act on the surface of the control volume or the control surface. Those include things like pressure forces, shear forces, maybe resultant forces, like for control volume against a wall, for example. So let me show these in the picture on the left-hand side. So here, let me draw a body force in blue. So there would be an example of a body force, like the weight of the fluid inside the control volume, if gravity was pointed downward there. And then let me draw some surface forces. So here would be like a pressure force. And then maybe we have some shear stresses acting over here. Some shear stresses. Maybe a resultant force that's a resultant from a combination of shear and pressure forces. Those are all examples of surface forces there. So those are all the terms in the linear momentum equation. And again, this version of the linear momentum equation is specifically for an inertial frame of reference. Now, why do I keep highlighting that? Well, what happens is when you use a coordinate system that's accelerating, so a non-inertial frame of reference, that might be a coordinate system that's rotating or accelerating rectilinearly, going in a straight line faster and faster, or moving along a curved path. When you deal with a non-inertial frame of reference or an accelerating coordinate system, then you get these fictitious forces that occur, things like a Coriolis force, centripetal kinds of forces. We'll talk about those in a separate lecture. But for now, we're dealing with a non-accelerating coordinate system, so we don't have to worry about those kinds of additional fictitious forces. All right, very good. A few notes that I want to make regarding the use of the linear momentum equation. So first of all, it's a vector equation. If you'll notice in the equation, each term is a vector. So in the first one, the velocity is a vector. The second term, there's another velocity, that's a vector. Now the url dot dA, that becomes a scalar because of the dot product, so we don't have to worry about that. But you still have this vector of the velocity at the control surface. And of course, body forces and surface forces are vectors. So even though it looks like one equation here, there are actually three equations buried inside. You've got one in the x direction, one in the y, and one in the z, for example, if you're using the Cartesian coordinate system. So just to show you that explicitly, if I wrote down the linear momentum equation in the x direction, it would look like this. I would be using the x component of the velocity. And the x component of the body forces and surface forces. And I would do the same thing in the y direction. And then ultimately would have the same thing in the z direction. Oops, let me fix that last y. And of course, if you're dealing with another type of coordinate system, let's say like a cylindrical coordinate system or spherical coordinate system, you could do the same idea. You just have three components to this equation in each of the three unit directions. Okay, so that's note number one. Let's see, note number two. When you use the linear momentum equation, just like when you use conservation of mass, you need to identify a control volume. So it's very important to highlight that. So identify the control volume that you're applying the linear momentum equation to. If you don't identify that control volume, then nobody really knows how you're using the linear momentum equation. The linear momentum equation is applied to a control volume. So you have to show that control volume. It'll help communicate the information to other people, and it'll also help you be a little more careful when you actually apply the various terms, try to solve for the various terms in the equation. So always clearly identify your control volume. If you find that you're uncomfortable identifying the control volume, you're not really sure, then that means you don't understand it that well and you need to learn it a little bit better. Unfortunately, I can't really give you an algorithm that tells you exactly what kind of control volume to use for every problem. The way you learn that is through experience and a lot of practice. The only thing I can kind of tell you right now is that you need to use a control volume that is related to what you're trying to find. So for example, with the jet engine, if I wanted to know the thrust from the jet engine, I'd draw a control volume around the jet engine. I wouldn't draw a control volume around up some bird off in the sky, right? It doesn't make any sense. It's not related to the problem. So you'd want to use a control volume that's related to what you're trying to find or what you're investigating. The other thing is you want to choose a control volume that makes the terms in the linear momentum equation a little easier to solve. So for example, in that mass flow rate term, the urel.dA, it's often convenient to put the control surface and velocity perpendicular to one another to make it a little easier to do the dot product. Because when you have the surface this direction, there's a normal vector to the surface, right? And then the normal vector and the velocity vector would be parallel to one another. It just makes doing the dot product easier. So choosing your control volume and control surface to help facilitate evaluation of the various terms is just a good idea. It just makes things easier for you. So identify your control volume. The other thing that you want to do is you want to identify your coordinate system or frame of reference. We'll say coordinate system here. Because the linear momentum equation depends heavily on what kind of coordinate system you're dealing with, you need to show what the coordinate system is, and it needs to be clear whether that coordinate system is not accelerating or is accelerating. We're going to be solving problems where we put coordinate systems on moving objects. So you need to make sure it's clearly identified that that coordinate system is on that moving object or it's fixed to the ground or somewhere else. So always identify your coordinate system. Again, if you don't identify it, then it's not clear to anyone else what it is you're doing. So make sure you do that. Item number 4 is draw free body diagrams. Again, since the linear momentum equation involves forces, you want to draw a free body diagram to show where those forces are. It's just, again, part of the communication issue of solving problems so that everybody knows what you're doing. And again, it'll help you make fewer mistakes if you do that. So draw free body diagrams. All right, another item. Carefully evaluate the velocities. Fix that last one, it looks sloppy. Okay, if you go back and look at the linear momentum equation, you'll see that there are 3 different velocities here. We have this first one, the u, x, y, z. That is the velocity of the pieces of fluid in the control volume. So here's a little piece of fluid in the control volume. So it's the velocity of that piece of fluid using our coordinate system, which I'll draw up here. So it's the velocity of that piece of fluid in the control volume, because the integral's over the control volume. That velocity of that piece of fluid with respect to that coordinate system. So that's what that first velocity is. The second velocity, the one in pink here, is the velocity of the piece of fluid at the control surface. So that would be a piece of fluid right here, for example. So that piece of fluid here is this one. It's evaluated on the control surface. And again, it's the velocity using our coordinate system here. The next one, u relative, we talked about before. This is just the velocity of the fluid at the control surface. So it's this velocity right here at the control surface. In fact, maybe I'll put a subscript CS there to make it clear that it's at the control surface. So it's the velocity of the fluid there minus the velocity of the control surface. Maybe the control surface is moving at that point. So this might be the velocity of the control surface here, and then this is the velocity of the fluid. Maybe there's some relative velocity between them. So you need to be careful in evaluating those three velocities. And again, I'll do some examples in separate videos where we can see the different velocities a little more clearly. But that's a common source of mistakes for people, is not really understanding what those different velocities are. So just be very careful of that. And the last item, and this is true just in general, state significant assumptions and how those assumptions affect your linear momentum equation. So, for example, many flows we analyze are steady. So if you're dealing with a steady flow, you would write that down and show that the steady flow means that the time rate of change of the linear momentum within the control volume is zero, that it's not changing with time. Steady means it's not changing with time, right? So you would show that, for example. So whatever assumptions you're making, just clearly write them down and show how they affect your governing equation. That's true for linear momentum as well as any other equation like conservation of mass or the first law. Okay, so those are the basics of the linear momentum equation. We're going to do some examples in other example videos, and then there'll be another lecture that talks about linear momentum using an accelerating coordinate system, namely coordinate systems that accelerate in a straight line at which we call rectilinear acceleration. So a coordinate system that's moving in a straight line in an ever increasing or decreasing speed. Okay, so we'll go ahead and end it there.